Hello everyone and welcome to chapter 4 which talks about integration. So imagine we have a curve like this and we were asked to find the area under the curve, which is here. Usually we can't do that using normal geometrical formulas. So this is where integrations comes in handy. What integration says is that we can divide this curve into small rectangles, very small rectangles. And then if we want to find the area under the curve, we just need to sum the small rectangles that goes from 0 here all the way to, let's say, infinity. So what integration really is just a sum over infinite values. And these values are changing because if we see here, the area under this part here would be different than the area under this part here because the values of the curve are continuously changing. But before we reach this point, we need to know what integration means in mathematics. Well, this is where we shall start. We start by section 4.1, which talks about antiderivatives. So what are antiderivatives? It's the first stepstone towards understanding integration. What we mean by antiderivatives is just antiderivatives. Derivatives, we know what's that. That's differentiation. So when we add the word anti, then we mean that we are undoing our differentiation, which means that we are trying to go back to the original function before we did differentiation. So let's say from the book, if we take the example f of x equal to 3x squared, this is a function that we've differentiated, right? And let's say we want to know what was the original function. Let's call it big F of x. So using our original knowledge of differentiation, we can tell that this came from x cubed, right? That's why we come in and say that f is an antiderivative. Generally speaking, we say that a function f is an antiderivative of f on an interval I when f prime of x, which is the derivative of this, shall give us f of x. So let's say if f of x prime ends up giving us f of x, which means that if we do x cubed and then we find 3x squared, x cubed prime, then this means that x cubed is an antiderivative of 3x squared, which means that f of x is an antiderivative of small f of x. But we can also see that we can have many functions other than x cubed which might give us 3x squared. That's why f of x, which is x cubed, is just one of the many antiderivatives of 3x squared. Because if we were to just add a constant, let's say here, we add another c, and then we differentiate, then there will be the derivative of x cubed plus c will be 3x squared plus the derivative of c, which is a constant. This will give us a 0 plus 0, which is 3x squared. That's why x cubed is just one of the many derivatives, antiderivatives of 3x squared. And that's what our first theorem says. It says that if we have an f of x, let's say this f of x here, an f of x, which is an antiderivative of small f of x, and then we have a g of x, which is also an antiderivative of f of x, then this means that g of x is just f of x plus a constant. This is the same as what we did here. So for instance, let's say we have a function f. We said, let's use the same example. So if our big f of x is x cubed, which is the antiderivative of 3x squared, as we said, the theorem says that we can have another function g of x, which is equal to x cubed plus a constant, whatever constant, let's say it's 3. So if we were to differentiate this function here, we'll also end up finding 3x squared. This means that g of x is also another antiderivative of small f of x. Through this theorem, we can find that any function f of x can be written, or the antiderivative of a function f of x can be written in the general form of f of x plus c. This is the general form of antiderivatives, because any antiderivative of f of x will be written as, just like we did here, x cubed plus a constant. Because if we change 3 here, let's say 2, it will also give us 3x squared. Let's say 4, also 3x squared, and so on. That's why when we want to find, let's say, the general solution or all the solutions of antiderivatives for f of x, we write it as f of x plus c, and then we note it as g of x. We say that g of x is equal to f of x plus c, and g of x is called the general antiderivatives. General antiderivative. And we call c, which is this constant here, the constant of integration. The constant of integration. And any solution that will be given as f of x plus c, let's say x squared plus c or x cubed plus c or whatever, this solution here, which is g of x, is called, let's say, it is called the general solution. General solution for what? For the differential equation. What is a differential equation? The differential equation is a function or an equation. The differential equation is an equation that involves f of x and its different derivatives. Let's say that we have a function f of x plus f prime of x plus f second prime of x equal to 0. This is called a differential equation. It involves a function f of x, its first derivative, and its second derivative. And it can go on all the way to f, let's say, n of x, which is the nth derivative of f of x. Differential equation may also involve the value x, which is the variable x. Let's say x plus f of x plus f prime, And in your book, they said that an example of a differential equation would be y prime equal to 3x. In here, y prime represents f prime, and then x is just this x here times a constant. This is one form of differential equations that we use. We either use y or f, it depends on our functions. We usually in maths we use y because it's an equation, so we try to avoid using f. which is a function in itself.